Hello there. In this video we're going to talk about one of the last important distributions that is usually discussed in a field of statistics course, and that is called the t-distribution. So previously in the videos, what have we talked about? So we're going to let z of k be normally associated random variables, namely standard normal distribution, and also recall that we let v be equal to the sum from k is equal to 1 to nu of zk, the quantity, squared. And we also realized that this was associated to a chi-square distribution. Alright, so in this video we're going to define similar things. So we're going to let z be a standard normal random variable, and we're going to let v be associated to a chi-square random variable with nu degrees of freedom. And we're going to define a new random variable, and we're going to call it t. So t is going to be defined to be equal to a standard normal random variable multiplied by the square root of the degrees of freedom divided by this random variable v. So one claim, and we're going to omit the proof, is that t follows a t distribution. So if we take any standard normal random variable and multiply by the square root of the degrees of freedom divided by a chi-square random variable, this variable follows a t distribution is what we call it. So what is a t distribution? So the t distribution has a PDF given by the following expression. So t of x is going to be equal to nu minus 1 divided by 2, the quantity factorial, divided by the square root of nu pi times nu divided by 2 minus 1, the quantity factorial. So keep in mind this, for some constant nu, is going to be a constant. And then the variable part of this expression is going to be 1 plus x squared divided by nu to the power negative nu plus 1 divided by 2. So this is what we call the t distribution. Slightly complicated, yes, but this distribution does have some interesting properties associated to it, and that's what we're going to talk about in this video. So if you put this expression into Desmos, and here nu corresponds to the degrees of freedom, then you're going to see a shape that should look fairly familiar to us. So if we put this in Desmos, this is pretty much the graph that we get. And if we recall the normal distribution, well, that's what this sort of looks like. And if we input the standard normal distribution on top of it, we actually see that these two graphs share a very close comparison with one another. Except that, if this red curve is the t-distribution, we see the normal distribution is slightly more higher, and the t-distribution tends to have a little bit more wider tails than the standard normal distribution does. And of course, if we increase the degrees of freedom, we see that this curve of red sort of gets closer to the purple curve, which is interesting, right? So we see as nu increases, the t-distribution gets closer to the standard normal distribution. So let's see if we can verify some of those claims. Alright, so let's do a couple examples. So example 1. Let us think about what the integral from 1 to 3 of the standard normal distribution of dz is going to be equal to. So this is the probability that a randomly selected z-score is in between 1 and 3 standard deviations on the right of the mean. So what is that going to be equal to? So let's calculate the integral. So the integral from 1 to 3 of the standard normal distribution, and we get that's going to be 0.1573. So 0.1573. So this is going to be a comparison value. And let's calculate the same integral under the t distribution with varying degrees of freedom. So we're going to look at the integral from 1 to 3 of t of x dx with, we're going to do 2 degrees of freedom. We're going to do the integral from 1 to 3 of the t distribution, and we're going to let it have 5 degrees of freedom. And then we're going to look at the same integral, 1 to 3, of the t distribution. And we're going to let that be equal to 20. And we're going to do t of x dx. And we're just going to jump to something really large, say 200. And we're going to see what happens to these values as the degrees of freedom approaches infinity. All right, so let's do that. So the integral under the t distribution from 1 to 3. So from 1 to 3 of the t distribution with respect to x, and we're going to set the degrees of freedom equal to 2. We say that this is equal to 0.1635 or 0.1636. These two values for the normal and the t distribution with 2 degrees of freedom are not that much different. They're within 1% of each other, which is okay. So if we increase this degrees of freedom up to 5, we get this equal to 0.1666. 1666. And if we increase the degrees of freedom to something like 20, we get this equal to 0.1611. 0.1611. And if we increase this up to 200, we get this as 0.1577. So now we're up to 3 decimal points in accuracy, and the 4th decimal place is where the difference is. So if we increase this even higher, then we should see convergence in the probabilities, right? So we see that t of mu of x converges in probability to the standard normal distribution as nu tends to infinity. So that's a conclusion that we see from this. Now, what if we just make this equal to 2000? Well, of course, Desmos has some computing power here, limitations, and that's namely arising from this factorial expression in the t distribution. But one can verify theoretically that this is actually the case. So you can try and increase it and see that these values are going to get closer. So if you take 300, for example, you see that they're, just a tad bit more closer. All right, so we see that this t distribution is getting closer to the normal distribution in terms of probabilities. Well, what about the actual values associated with these probabilities? So let's look at things in another perspective. So let us assume we have some normal distribution. So this is going to be n of z. And let us assume this area here, symmetric about 0. Let us assume this area is equal to 0.35. So in the previous exercise, we figured out, okay, how are we going to find out what the z of x value is equal to? So we can find that by finding the x-intercepts of an auxiliary equation. So let us do that. So let's get rid of these integrals since they're not really useful to us now. I'm going to define a new function, f of z of x. And this is going to be equal to the integral from minus zx to zx, since we're on a symmetric interval of interest, of the standard normal distribution, and of z dz, minus, and we want that area to be equal to 0.35. So we get this as 0.4538. So 0.4538. So let us now see what happens for the t distribution. So if we take the same exact area, also symmetric about 0, that's one of the special properties of the t distribution. So let us, this curve be the t of x distribution. Let us assume this is 3.5. Now, of course, t of x is dependent on some degrees of freedom. So what is this value here? And I'm going to call it t of x is equal to. So let us choose, say, degrees of freedom is equal to 30. All right, so what is that value going to be approximately equal to? All right, so let us change our degrees of freedom. Let's go to, what did we say, 30? Yeah. Let's see here. Let's define g of t of x. That's going to be equal to the integral from minus t sub x to t sub x of our t distribution t of x. And we want that area to be equal to 0.35. Now let's delete this blue so there's no overlapping regions. So we get this is 0.4584. So we see that there is a real close connection to these values. And let us increase it just a tad bit. So we'll do the same exact region. So let this be 0.35. Let this be the t of x distribution. And let us assume that the degrees of freedom is equal to 100. What is going to be my corresponding t value that associates to that? So that's just a quick change of our degrees of freedom. And we get that this value here is going to be 0.4551. So we see that these values are pretty much, these values are decreasing, getting closer to this z value. So what do we see? We see that the t distribution with new degrees of freedom is converging in values to the normal distribution. And that's as nu goes to infinity. So what is the application of this t distribution? Well, that is what we will talk about in a later video. But overall, this is how you find probabilities and t values associated with a t distribution.